We are going to solve exercise number 6 of the handout for the chapter 1. In this exercise, we will do some more exercise. Sorry for the redundancy on the convolution and the properties of linear systems in discrete time. So let's get started. So this is exercise number 6. So in this exercise, they tell us that we consider a system on which the output ydn can be calculated from the input xdn doing basically this operation, which is we take the input and we convolve the input with itself. So applying the definition of the operation convolution, this is the summatory from k equal minus infinite to plus infinite of the signal, one of the signals, x decay, x of k, multiplied by x of n minus k. So that's a very peculiar system because looks like somehow the impulse response of the system itself looks like it's the input signal itself. So it's a very strange system because somehow the response of the system changes depending on the input. So let's see. Let's study the system and see what surprises we can find. So in A, they ask us to demonstrate if the system is linear, if the system also is time invariant. The system, they ask us to see if it is causal and if it is stable or not. So let's see. Let's get started. In each of the cases, what we do is we apply the definition, and as we will do this without knowing the impulse response of the system, because it's a bit strange, because as I said before, the input response, the output to the impulse input is depends on the input itself. So let's try to do that just using the definition of each of these properties without using the impulse response. Okay, so let's go for the linearity first. Linearity. Is the system linear or not? So for that, you know that what we do is we take an input x1dn, for which we will get an output at I1 of n. We take another input x2dn, for which we will get an output y2 of n. And what we do is we make the linear combination of these two outputs. So we take a coefficient alpha multiplied by x1 plus another coefficient beta multiplied by x2. Okay, and we called this over new input that we have created. Let's call it x dn. And this combination, linear combination, will output a signal ydn. And what we wonder, if the system is linear, then this output to this linear combination of inputs should be exactly the same linear combination as if each of these x1 and x2 signals were input to the system individually. Okay, we have to check that. So let's do that, ydn, and then we apply the definition, ydn, the output is the summatory from k minus infinite to plus infinite of the signal that we input multiplied by the same signal but in n minus k. So for xdn, we take the xdn that we have created, which is the linear combination of x1 and x2. So this will be the summatory from k minus infinite to plus infinite of the first x decay, and x decay is the linear combination alpha x1 dn, alpha x1 dn plus beta x2 dn of n multiply by the input but in n minus k. So alpha x1 in n minus k plus beta in x2 of n minus k. So that is the expression. So now we operate. So we multiply these two binomial terms. So the first one will be alpha x1 dn multiplied by alpha x1 in n minus k. So will be alpha squared that goes out of the summatory. So alpha squared summatory, I won't put here the k's as well, you know, is the summatory in k from minus infinite to infinite of x1 k x1 and minus k plus second term multiplied by second term will be beta squared summatory in k of x2 dn x2n multiplied by x2 n minus k, and then we have cross terms that will be alpha x1 n multiplied by beta x1 n minus k plus and another term which is beta x2 dn multiplied by the other cross term that will be multiplied by alpha x1 n 1 minus k. So the first term will be AB, we take out of the integral of the summatory, AB summatory in k x1k x2 n minus k plus this other term which will be alpha beta also, or beta alpha you can say, summatory in k of x2 k multiplied by x1 n minus k. So this will be just, you can see, the summatory in k of x1 dk multiplied by x1 n minus k is the convolution of x1 with x1. So this will be alpha square y1 dn for the using the definition of the system itself. The second term will be beta square multiplied by the definition of I2 dn. Okay, but we have two cross terms here. The first cross term will be alpha beta, and this cross term here, let me check, this cross term is the convolution of x1 with x2. So this will be the convolution of x1 with x2, and the second term will be alpha beta, the convolution of x2 with x1. These these two terms you can put together because of the commutativity property, the commutativity property of the convolution. This is 2 times alpha beta x1 convolve with x2 So basically, this is different. This is different from what will be just the pure convolution of the linear combination of the output, which will be only this. We have an additional term, which is basically that one. So this is not IDN. This is not IDN. There is, as I said before, this additional term. So the system is not linear. Okay. So this strange system which takes the value of the input and uses this value just to somehow calculate the input. This is not a linear system. Okay, let's go for the second property. Is a time invariant? Is time invariant? Is the system time invariant? So let's remember that time invariant means that if we have an x1 dn signal and we get a y1 of n output, we can take another signal which is x1 dn, but we delay it. If we create this signal and we input this signal into the system, we should get, if the system is time invariant, we should get an output which is exactly the same as the input without the delay, but just the output being delayed the same amount. So this is what we have to check, just applying the raw definition. Okay, so let's go ahead. Y of n, for definition of the system itself, is x dn convolve with x dn. So in this case, x dn is the x1 delayed in n0. So this will be x1 delayed n0 samples convolve with x1 delayed n0 samples. Okay, so we can write this using the property of the convolution with a delta. This is exactly x1 without delay, but convolve with a delta delayed in n0 samples. Again, because of the property of convolving a signal with a delta. If you convolve a signal with a delta, what you do is you delay the signal where the point where the delta was, or the same number of units that the delta was delayed. So this is a convolve with x1 delayed, which again is x1 dn without delay, but convolve with a delta delayed n0 units. Okay, so now using the properties of the associativity property of the convolution, we will have x1 dn. We can write this x1 dn convolve with x1 dn, and then we will have delta n minus n0 convolve with L delta n minus n0. So in this case, we can, for example, consider the first delta as if it were, let's say, a function, whatever function. And so we will have the same situation. We will have a function here convolve with a delta, which is delayed n0 units. So what do we have to do? We have to take the function, which is again a delta, n minus n0, and we delay the same amount that the delta we are convolving with. So we delay the delta, this delta, n0 units. So as it was delayed n0 units already, so it's like delaying 2 times n0 units. Okay, so that's it. So now, if we convolve, for example, these two terms, so this will be x1 dn convolve with x1 delayed, in this case, the same amount that the delta is, so delayed to n0 units. Okay. Yes, I am doing right, yes. So basically you can see that y(n), the output, is x1(n) convolved with x1 but not delayed in 0 units, but not delayed, not convolved with itself, but convolved with the signal delayed 2 and 0 units. So basically what this means is that the system is not invariant. Okay? So let's check if the system is causal. So the system is causal. Remember that if basically to calculate the output, I don't take any value in the future of the input, So let's check. So how do I calculate the output? Anytime. So anytime I calculate the output by summing over all the values of k from -infinite to +infinite of the input multiplied by the input on n minus k. So this summatory typically has a lot of terms coming from infinite, but for example, we can stop and check that, for example, for k equal to -1, we will have x in -1 multiplied by x in n minus -1, so n plus 1. The next term, for example, will be x in k equal to 0 multiplied by xdn plus, a lot of terms to the right. But what we can see over here is that we are using a term to calculate ydn that is in the future of the signal. Okay, so x in n plus 1 is the instant xdn 1 second later. So basically, as we are using a future value of xdn to calculate the current value of ydn, the system is not causal. Okay, let's go for the last one. Is the system stable? So most probably the system, if the system is not LTI, the most probable thing is that the system is not stable. It's quite hard always to demonstrate that the system is not stable, or in other words, that if we input a signal that is bounded, the output will be bounded. So stable also is a BIBO system, which is bounded input, bounded output. So it's very hard. Again, most likely the system will not be stable. So it's quite hard to demonstrate mathematically that if the system is bounded, the output may be not bounded. So typically in these cases where we strongly suspect that the system is not stable, because in this case again is not LTI, is the best strategy is to try to find a counterexample. So you find a counterexample which is a bounded input signal, and you calculate the output, and you see that the output is not stable, is not bounded, and by doing this you have demonstrated that the system is not stable. But so that's my recommendation. Let's try to find a signal that is bounded, and we will see that this signal creates an unbounded output, and that's the demonstration. So what other hints can I give you to find this input bounded input that creates an unbounded output? So in this case, what I will recommend is trying typical signals. For example, a typical signal that is used to demonstrate these types of things is UDN. So the Heaviside step is a very, very good signal to demonstrate this type of things, because it's a bounded input, but typically generates unbounded output when they are entered in not BIBO stable systems. So let's do that. If we use the signal, basically UDN, you know what type of signal it is. It's like that, the Heaviside step. So you have this value where this is 0, this is 1, this is 2, this is 3, all the way to the right. And basically we have to check, calculate YDN, that in this case is, by definition, is the input convolve with itself. Okay, we have to calculate that. This is a very easy calculation of a convolution. You can do that analytically or not. For example, we will do that visually. To do the convolution, remember that what you have to do is you have to fix one of the signals. So in this case, both signals are the same. So we think that UDN, for example, is this one. The other UDN, what we have to do is we reflect to the left and we delay tau units. So if we delay the signal reflect to the left, basically what we will have is the Heaviside step to the left, and then we move to the left units and we start moving to the right and finding out when this signal that is moved to the right encounters this signal, and then start multiplying each of the samples. Okay, so it's clear that when we delay to the left, so when n is negative, basically the Heaviside step on the left will multiply to 0 with the first signal, because the first signal is 0, the other signal will be over here. So basically we will multiply in zeros all the way when n is negative. So basically in this range, y of n is 0. Okay, but what happens when n is more or equal than 0? In this case, we'll have a situation where the Heaviside step that we had on the left, going to the right, is like that, has come to this range of values, and in this case we will be multiplying these figures, these two series, 1 multiplied by 1, 1 multiplied by 1, 1 multiplied by 1, so we will need to add 1 plus 1 plus 1 plus 1, and in this case then the YDN basically will be summing on k, from k equals 0 to n, basically a summatory of 1s. So this is the n plus 1, and that's it. We have the convolution. So basically YDN, you can see, is n plus 1 UDN. Okay. So this, remember, is the ramp function. We have seen that in other exercise. So basically what we have is on 0, we have the value 1. On 1, we have 2. On 2, we have 3. And all the way up. So it's a ramp, is the ramp function, but somehow displays to the right 1 unit. Okay, the ramp function displays to the right 1 unit. Okay, so we are done. Basically, we had a bounded input, which was UDN, and we have demonstrated that the output is unbounded, because the ramp function is unbounded. So basically what we have demonstrated is that the system is not stable. We found a counterexample. Not stable. Okay, so let's keep moving with the exercise. Now in number B, they say us that let's think on an input which is xdn equal to udn minus udn of n minus 5. And where udn is the discrete time Heaviside step. And we are asked to calculate analytically and sketch y of n. Okay. So we can do that either way, graphically or analytically. So graphically, I will let it to you. It's very, very easy because basically what you need to do is first you need to see which type of signal this is. So it's very easy to see because basically you can see 0, 1, 2, 3, 4, and 5. 5. Basically this signal is this one. It's like a pi signal. It's a pi signal because we are using u of n that goes to the right to infinite, and then on n minus 5 we subtract another u the n. So this is basically the signal itself. Sorry, here I made a mistake, sorry. In 5 is 0. Because u of n minus 5 is 1 exactly in 5. So there the two signals will cancel out. So basically that's the minus 1, minus 2, and then to the right 6 will be 0. So this is the signal xdn. So it's very easy to calculate the convolution of the signal with itself. So y of n, you know, is the convolution of the input with itself. So what you have to do is to do the convolution of this signal with itself. So again, this is an exercise for you. I encourage you to do it, let's say, graphically. But let's do that analytically. Okay, let's do that. So how do we do that analytically? So very easy. Y of n is, again, as I said before, is convolving xdn with xdn. So xdn is u of n minus u on n minus 5 convolve with itself. Okay, so we now apply, sorry, this is a minus here. So we now apply the property, which is the distribution of the convolution with respect to the plus or minus property or operation of the signals, and we will have u the n convolve with u of n. Then we will have u of n convolve with u on n minus 5. We will have u on n minus 5 convolve with u the n, and then we will have u on n minus 5 convolve with u on n minus 5. Okay, so we have just operated the parentheses. So if we group these cross terms over here, we'll have u the n convolve with u the n minus 2 times u the n u of n convolve with u on n minus 5. But we will write u on n minus 5 as u on n convolve with delta on n minus 5. Why we are doing that? Because then we have here two UDNs that we can very easily operate. Okay, we do that with the last term as well. So in the last term we will have u the n convolve with u We have in this case 2u on n minus 5, so then we will have u the n convolve with delta on n minus 5, convolve again with delta on n minus 5. Okay? And now we do the following thing. We know from the counterexample that we did that convolving with itself u the n gives as a result the ramp function displays 1 unit. So is n plus 1 u the n. And we will substitute in the previous line u the n convolve with u the n with n plus 1 u the n. So let's do that. So the first term is u the n convolve with u the n, so we substitute that with n plus 1 u the n minus 2 times, and again we have another u the n convolve with u the n, so we also put n plus 1 u the n convolve with delta on n minus 5. And this we can also operate, so we have again a function that is convolved with a delta delay 5 units. So we just delay 5 units the function itself. So this will be n plus 1 minus 5 on u n minus 5. And this is n minus 4 multiplied by u on n minus 5. Now we go for the next term. So we have u the n convolve with u the n. So again, this will be n plus 1 u the n convolve with delta on n minus 5 convolve with delta on n minus 5. So basically here the first term is exactly the same term that we have over here, so we can just copy this result here, and we just need to do the convolution of this with delta on n minus 5. So we just delay 5 units the result. So n minus 4 delay 5 units of u on n minus 5 delay 5 units, so n minus 10. So this will be n minus 9 multiplied by u on n minus 10. So this is just operating and paying attention not to make mistakes, of course. So at the end, what we have is y the n equals to n plus 1 u the n minus 2 times n minus 4 u on n minus 5 plus n minus 9 multiplied by u on n minus 10. So let's take a look to this function, and so that we can draw it. So y the n. So when n is less than 0, okay, obviously all the u the n's, that is either starting on 0 or delayed to the right, basically will be 0. So here y the n is 0 for any n less than 0. What happens when n starts on 0, right on 0? So the only term that we will have is that 1. So in this case, we will have n plus 1, again, for what? Well, for n when it's right starting on 0. Up to what point? Well, up to the point that the next signal comes into play. The next signal comes into play in 5. So in this case, is up to 5. Right in 5, we will have the next signal running into place. And then we will have the first signal, n plus 1. And now the second signal, which is minus 2 multiplying to n minus 4. Okay, and this is 9 minus n. And this will be valid starting on 5 up to the point where the next signal starts, which starts in 10. So this will be up to 10, not including 10. What happens in 10? In 10, we will have the signal that we had before, so 9 minus I, and now coming into play the next one, which is n minus 9. So this is 0. So for n more or equal than 0, basically the signal is 0. So let's draw it. This is the picture of the function. So we will go all the way to 10. And basically we have a ramp function here. It's going to be a triangle function. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 4, 3, 2, 1, 0, and 0. Okay, this is the picture of the final signal. And again, you could have done that doing the convolution graphically, as I said before, but also analytically. Thanks for watching.